In this video, we're going to introduce the idea of calculating an area that is bounded between two curves on our graph. Okay, so previously we have looked at the area problem where we're given just some function and we have been asked to calculate the area from some value of x equal to a up to some value of x equal to b under that graph. Okay, and to calculate that area, we discovered that what we were able to do is just to take the integral from a to b of whatever that function is. And that would give us the area that was bounded by the x-axis and the function f. Okay, so now we want to look at this new problem where we want to be given two functions on our graph, and they want us to calculate the area that is bounded between the two of them. So I'm going to add a new function to this graph. And they want us to calculate this area that is bounded in between these two graphs. Okay, so the idea that we had back in the area problem, back in chapter 4, was that essentially we were taking just a rectangle and we were saying that the area of a rectangle was base times height, and we accumulated a whole bunch of those rectangles, which meant that we had to take a limit of a sum as the number of rectangles went to infinity, which we then turned into the integral problem. Okay, so we're going to use the same idea here, where we're going to look at one of those rectangles, a cross section, and if we can calculate the area of one of these rectangles, then we will be able to take infinitely many of those rectangles and calculate the area bounded between f and g. Okay, so when we're looking at this rectangle, we know that the length of the base of our rectangle is going to be delta x because we are measuring some change in x. Okay, when we look at the height of this rectangle, now we are looking at the distance from here to here, so just the height of our rectangle. So when we look back at our original picture, we are really looking at this length from this point down to this point, which are just the function values. Okay, so our height of these rectangles is just going to be equal to whatever this function is here on top minus the function that is on the bottom. So top function minus the bottom function. And for notation purposes, I'm going to label this top function as y sub t, so y top. And then for my bottom function, I'm going to label that as y sub b. All right, and now we want to just take a whole bunch of these rectangles and we want to sum them up, which means that we are really just taking an integral from point A to point B, or in this case, these two functions intersect each other. They happen to intersect at A and B. So wherever those intersection points are, we're going to integrate from A to B, or the integral that they give, the interval that they give you, whichever the problem stipulates. And we want the area of each of these rectangles. Well, the height we just said was y top minus y bottom. And we said that the length of the base of each rectangle was delta x, which is the same thing as dx. Okay, this will give us the area bounded between two curves. And of course, we have to assume that we have continuous and integrable functions to be able to do this. Okay, so let's go ahead and look at an example. We're going to find the area of the region bounded by y equals square root of x and y equals x squared. Okay, so the first thing that you're going to want to do is sketch a picture so you know what our particular region looks like. So we're going to sketch a graph. And they did not give us any sort of interval to work on, so we're assuming that these graphs are going to intersect somewhere to give us our boundary points. Okay, so we know that we have the square root graph, which will look something like this. And we've got the x squared graph, which will look like something like this. And we're looking at the area bounded between the two. Okay, so in order to know what our limits of integration are, we need to know what are these intersection points. So step 2, we're going to find the intersection points. So to find the intersection points, we're going to go ahead and set the two functions equal to each other. X squared is equal to the square root of x. And from this, we know that x is going to be equal to 0 or 1. Okay, so now that gives us our x values in which we will do our integrating. All right, so now if we look at our cross-section or one of these representative rectangles, we see that the length of the base of our rectangle is delta x, and then the height of that rectangle is going to be equal to y top minus y bottom. And y top in this case is this function here, which is our square root of x, and our y bottom, this function here, is our x squared. Okay, so this will give us our height. So now setting up our area problem, our area is going to just be the sum of all those rectangles going on the x-axis from 0 up to 1 of the height of each of those rectangles, which is the square root of x minus x squared, times the length of the base of each rectangle, which was delta x, and that is the same thing as dx. Okay, and now we go ahead and we solve the problem. So now we go ahead and integrate. So square root of x, that will give us 2/3 x to the 3/2 minus x cubed over 3. And we are integrating from 0 to 1, so we evaluate from 0 to 1. And now we go ahead and make our substitutions. So from this we get 2/3, and then we plug in 0 and we get 0 minus 0. Okay, so for our final answer, the area bounded between the two curves is 1/3, and that'll be units squared. Okay, so example 2, find the area bounded by x equals 0 and the first intersection of y equals sine of x and y equals cosine x. Okay, so we'll first go ahead and sketch the region. Let's see here. So we're bounded by x equals 0, so that is just the y-axis. We want the function y equals sine of x. And we want the function cosine of x. Okay, and we want this to be bounded by x equals 0, and then they want us to close off at this first intersection. So the area in question is right here. All right, so what we need to know is we need to know what is this point here, where do sine and cosine intersect each other, because that will be our other limit of integration. So sine and cosine intersect each other when we're at pi over 4. And then 0 is our other boundary point. Okay, so our limits of integration go from 0 to pi over 4. Okay, so next we'll go ahead and look at our representative rectangle. And we see that the length of the base of our rectangle, again, is delta x, or dx. And the height of our rectangle is going to be y top minus y bottom. So when we go and we look at what the top function is, top function here is cosine. And then the bottom function is sine. Okay, and that will give us the height of each rectangle. Okay, so now plugging in for area. The area is going to be the sum of all rectangles, so that's the integral from 0 to pi over 4 of the height of our rectangles, which was cosine of x minus sine of x, times the length of the base of our rectangle, dx. And now we'll go ahead and do our integrating. So antiderivative for cosine of x minus sine x is going to be sine x plus cosine. And we want to evaluate that from 0 to pi over 4. So plugging in pi over 4, we have sine of pi over 4 plus cosine of pi over 4, minus plugging in 0, sine of 0 plus cosine of 0. And now plugging in our values for these, sine of pi over 4 is square root of 2 over 2 minus cosine of pi over 4, square root of 2 over 2, and then minus sine of 0, so that's going to be 0, and then cosine of 0 is 1. So that gives us an exact answer of square root of 2 minus 1. And then from there, if you needed a decimal, you could get a decimal. So this would be about 0.414. Okay, so that's just the introduction of how to calculate area that is bounded by two curves. What we'll be looking at next, these basic ones, we'll look at where curves intersect each other more than one time, so you'll form multiple areas. And then we'll also look at some examples of when it will be better to take our rectangles, so our representative rectangles, instead of these rectangles going up and down where you have dx as your base, we can take these rectangles and flip them the other direction and turn it into a dy problem. Okay, so that'll be in the next video, and we'll see you next time.